Hello everyone, this is Team Titans presenting you our study on the research paper Deja Vu Continual Model Generalization for Unseen Domains. So let me give you a brief overview of our objective. The thing is, the traditional ML or a deep learning model is used to make predictions on a particular data or data with same distribution. But in real life, the model might face challenges like domain shift, where the model is asked to predict on some unseen domains. And initially, the model won't make robust predictions due to the shift, and this period is known as unfamiliar period. Our motivation is to develop a model which overcomes these challenges and quickly adapts itself to new domains. And to do so, we are evaluating our model based on three main matrices, namely TDG, which is the target domain generalization, mainly to evaluate the model during the unfamiliar period, and TDN, namely target domain adaptation, which is the after adaptation period. And to mitigate the forgetting, we use the forgetting alleviation metric. This is the brief overview of our measuring matrices. So next is the frameworks of our model. Our model is named as RATP, and the components of our frameworks are the random mix, where we generate augmented data from the original data to support TDG. Next is the top square pseudo labeling, which is to improve the TDS score of the model. And next is the prototype contrastive alignment, domain alignment for TDG, TD, and forgetting alleviation. The detailed explanation of our frameworks. First is random mix. This, as I said before, this main purpose is to boost the unfamiliar target generalization. The mechanism goes as follows, where it uses autoencoders and then applies mixup to generate data with a greater variability, which eventually helps in generalization. And we can see that impact of random mix on performance of RATP on digits dataset. The TDG of RATP is 86.8%, which is comparatively higher to other models. Next is the top square pseudo labeling, which helps in target domain adaptation. The approach is we select top 50% of samples based on softmax confidence and then uh, construct the centroid. The centroid construction formula is given below. And the performance impact of top square pseudo labeling is also visible here. The RATP TDS score is 86.8% on digits dataset, which is comparatively higher than other datasets, other models. Next is the prototype contrast alignment. The main objective of this is to align distribution across the domains for consistent TDG, TD, and FA scores. The implementation goes as follows, where we use the classifier neuron weights as prototypes for class representation across all the domains, and then we minimize the contrastive loss. The effectiveness is visible where FA retention on digits of RATP is comparatively higher than quota model. So now our experimental setup is as follows. We are using five digits dataset, PACS and domainnet datasets to evaluate our model, and the matrices are TDG, TD, and FA as mentioned before. And we have also presented our baseline comparisons with other models. So these are the results of RATP model on different datasets, and we can see that RATP has almost outperformed all other baseline models in all the metric aspects. So now this is a very important study, which is to emphasize the importance of components used in the RATP model. So these graphs are plotted by evaluating the performance of model where we have you not used the random mix, and we can see that the shaded region is the region where the model has been trained without using random mix, and we can see that there is a significant decrease in the model's performance. So hence each and every framework used in RATP is of great importance, and removal of each of these would generate a decrease in performance on each of the metric. So the conclusion is RATP has effectively managed to overcome the domain shift problems, achieving high TDG and TDS scores while a substantial FA score. So there are various applications of this in real life. such as surveillance, autonomous driving, and medical diagnostics, where environments constantly keep on evolving. And there are also some future applications of this where we can extend it to some other fields. Thank you.